Welcome everyone to this week's Science News. Today we'll talk about raisins. Yes, raisins. Quasars with dark matter halos, pink diamonds, the last moments of a dying satellite, a new type of qubit, maybe. How to measure the length of the day with lasers, a new treatment method for brain cancer that's got something to do with quantum mechanics, whether climate change drives migration, and of course, the telephone will ring. Before we start, I have a service announcement, so to speak, which is that this video comes with a quiz on quizwithit.com. This lets you check how much you remember, and you can collect points by taking quizzes for our other videos. This app is brand new and we're still working on it. If you subscribe, this will help us develop the app further and make it available to other creators. So give it a try and let us know what you think. The most fun paper of the week comes from Saverio Spagnoli, a professor of mathematics at the University of Wisconsin-Madison, and his collaborators. They studied the behavior of raisins in carbonated water. They got interested in this after Spagnoli and his young daughter observed raisins dancing in water. The gas attached to the raisins, and that lifted them up, and when they reached the surface, the bubbles at the top popped, causing the raisins to sink, bob and start rising again. To study the effect, Spagnoli and his collaborators 3D printed some small spheres and submerged them in carbonated water. Carbonated water is supersaturated with carbon dioxide. This basically means there's too much carbon dioxide in the water for it to stay dissolved at normal pressure. It stays in the water only so long as you keep it in a closed bottle, which exerts pressure. If you remove the pressure, it bubbles out, and those bubbles usually form around some kind of condensation seed, like a crack or a rough surface, or a raisin. The researchers now observed that when the spheres were kept stationary, the bubbles grew on the surface fairly regularly. When the spheres were allowed to move freely, however, their bubbles allowed them to rise to the top and then sink back down. This continued as long as the concentration of gas in the liquid was high enough so that the bubbles could lift the spheres. They then created a computer simulation to quantify the effect. Dancing raisins probably won't have a lot of applications, but supersaturated solutions do occur in the real world, such as with gas bubbles that push magma towards the surface of a volcano. So it's not an entirely academic question. Maybe that's why we speak of raisin a question? New research out of Japan shows that dark matter halos around quasars don't grow as expected, creating yet another puzzle in cosmology. A quasar is a type of active galactic nucleus. That's a supermassive black hole which draws in matter, heats it up, and in that process radiates off a lot of energy. Quasars are incredibly bright, but don't quite look like stars. That's why they're called quasars. They're quasi-stars. But the universe was not born with quasars all in place. Physicists believe that it takes dark matter plus time to make a quasar. You see, if dark matter exists, which it may not, then there's much more of this matter in the universe than the normal type of matter that quasars and we are made of. The current estimates say about 80% of matter in the universe is dark matter. But this is the average for the entire universe. Galaxies are usually more than 90% dark matter. Yes, the Milky Way too is more than 90% dark matter, if dark matter exists, which it may not. Dark matter in galaxies is believed to not form disks, but spherical clouds that spread out far beyond the distribution of the visible stars. These clouds are called dark matter halos. Now, if normal matter begins to collapse under the pull of its own gravity, it gets hot, and that creates radiation, and that radiation creates pressure. This pressure acts against the collapse. Dark matter doesn't create radiation, pattern, which is why it clumps faster in the early universe. And since there's so much dark matter around, once it's clumped, it attracts the normal matter, which also clumps. This creates galaxies, and some of those galaxies will go on to form supermassive black holes in their center. So now you have a quasar in a dark matter halo. The amount of dark matter in the halo affects how the galaxies are distributed. And since the quasars sit in the halo, you can use the distribution of quasars to approximately infer the mass of the dark matter halos. This was previously done for nearby quasars, but in the new paper they looked at about 100 really far away quasars at around a redshift of 6. That's about 8 billion light years away. They found that quasars at that distance tend to have dark matter halos with a mass of roughly 10 trillion times the mass of our Sun. The weird thing is now that that's about the same as the halo masses of the much younger quasars. This is somewhat confusing because as the universe gets older, the dark matter halos combine and grow and keep on growing. You'd expect that younger quasars have larger halos. They say that part of the reason may be that their sample is biased, especially because they've missed some of the fainter quasars. They also say there might be some kind of feedback from the quasars into their environment that prevents them from growing, kind of like YouTube channels stop growing because they appeal to people who don't like large YouTube channels. This one isn't a huge problem for astrophysicists because the growth of quasars quite plausibly depends on a lot of variables that are not very well known. However, to me, it generally adds to the feeling that something isn't quite right with this dark matter story, and that at the very least it's more complicated than we thought it is. What do you think, Albert? Researchers from Curtin University in Australia say they figured out how to find pink diamonds. Natural diamonds form when carbon encounters extreme heat and pressure deep within Earth. Pink diamonds are incredibly rare and therefore especially sought for. The color is caused by defects in the crystal lattice that change how they absorb light. Geologists have known for some while that pink diamonds are more likely to be found in areas where tectonic plates meet, because creating those lattice defects requires a lot of force that the tectonic plates supply. But why they're found in some such areas and not others has remained somewhat unclear. For the new paper now, the scientists studied the geological past of the Argyle diamond mine, which closed in 2020. It was located in the East Kimberley region of Western Australia and was famous in particular for its pink diamonds. The researchers used ultra-thin laser beams to evaporate rocks in the region and date them. They found the region to be roughly 1.3 billion years old. That's 100 million years older than previously believed. This is relevant because it means that the region likely formed when an ancient supercontinent called Nuna broke apart. The researchers say this created gaps in the Earth's crust that allowed the flow of magma. When the magma rose to the surface, it likely brought the pink diamonds with it. Now that we have a better idea of where pink diamonds come from, this might give mining companies a clue what conditions to look for to find more pink diamonds. It's not all that easy though, because such old volcanoes can be difficult to recognize after they've been covered up by sediments for billions of years. So maybe have a look under the couch. The European Space Agency's Aeolus satellite has met its demise. After nearly 5 years of collecting wind data, ESA guided the satellite back through the atmosphere over the Antarctic, where it burnt up. Aeolus was the first satellite mission to capture global data for wind patterns, able to measure wind speed to an accuracy of just 2 meters per second. But after 4 years, 11 months and 6 days of collecting data, it ran out of fuel and dropped down from the sky, a fate that'll be familiar to many graduate students. Today's international regulations require that satellites must be removed from orbit within 25 years of their retirement, and spacecraft are now built to minimize the risk of damage upon re-entering Earth's atmosphere. But Aeolus was designed in the 1990s, a simpler time when people worried about kids getting addicted to Tamagotchis, not about space debris falling onto their heads. So this was a much anticipated event. The mission team couldn't leave the satellite in space, but it's not great for international relations to let space junk randomly fall down somewhere. Not that China seems to care much, but Europe isn't China, and ESA therefore decided to let Aeolus re-enter the atmosphere over the Antarctic, because fuck those penguins. In the end, it all went well. The satellite re-entered Earth's atmosphere over Antarctica as planned and turned into a bright hot fireball for roughly 2 minutes before burning up more or less entirely. That's the future of retirement in Europe. They'll burn you up above Antarctica. Physicists in Texas claim to have developed a highly magnetic material that could make quantum computing at room temperature possible. That's what the press release says anyway. Most of the existing quantum computers must remain in super cold environments to prevent quantum entanglement from fading away. The cost and inconvenience of this extreme cooling is currently the major obstacle to building larger quantum computers. In the new paper now, the researchers report they've created a material that's super paramagnetic. A paramagnetic material is different from the usual magnets that you have on your fridge or so, in that its magnetism only appears in response to a magnetic field. Paramagnetism can therefore be controlled, which makes it interesting for computing. Superparamagnets are strong paramagnets. The ones that the researchers created are 100 times more magnetic than iron, and they maintain these properties at room temperature. This is really interesting because such tiny controllable magnets could be used to store information and process it. So yes, it could be useful for computing. But this doesn't mean we can now build room temperature quantum computers. It takes a little more to do that. Most importantly, you'd have to demonstrate that those bits of information can be entangled and that those quantum links remain stable at room temperature. So yeah, it's interesting, but not as interesting as the press release made it sound. Hello? Mr. Rishi Sunak. Because someone asked me the other day, who's this Richie who keeps calling? Yes, I saw that. No heavy-handed measures like sorting your rubbish into 7 bins. I think that's great. There's no way I could sort the rubbish in my inbox with just 7 bins. Thanks for calling in. Having a long day? It's not just a saying. Some days are really longer than others. But just how much? Thanks to scientists in Germany and New Zealand, it's now simpler than ever to measure how long our days are. The Earth doesn't always rotate at exactly the same speed. It's because it's not just one big solid ball, but has parts sloshing around. The atmosphere, water, and also the liquid core don't move at the same rate as the surface. But since angular momentum is conserved, if some of the sloshy bits move faster, Earth has to rotate a little slower. Granted, it's not a huge effect, but it can be a few milliseconds a day. Enter Big G, the laser gyroscope at the Geodetic Observatory Wetzel in Germany. Big G uses laser beams whose wavelengths are known very exactly. The light travels several meters around in a square in 2 opposite directions. Depending on how the direction of the laser light is aligned with the rotation of Earth, the wavelength of the light is either stretched or squeezed. When the 2 beams come together again, the difference in wavelength encodes the speed of rotation of Earth. That way, scientists have been able to pin down the length of the day to a precision of a few milliseconds. The precision is comparable to other methods, but the nice thing about this method is that it delivers data about the rotational speed within an hour. So if you feel like you've had a long day, all you need is a room with a laser gyroscope to make your case. A multidisciplinary team of researchers in the UK has developed a new method of brain tumour treatment. They call it the first quantum therapeutic for cancer. Well, wow. I don't normally talk about cancer treatment, but how could I resist something with quantum in it? The idea is this. Cells use quantum effects. Notably, this is quantum tunneling of electrons, which plays a role for some chemical reactions. The researchers use nanoscopic gold particles that they put into an electric field, which polarizes the particles. The gold nanoparticles have other molecules attached to them, which can launch some of those electron transfers, and that can damage cells, which then die. They call these things bio-nanoantennas. The researchers measured the effects of these nanoantennas using several cell cultures, some cancerous and some not. They found that the cells absorbed the nanoparticles readily within 8 hours. Then they exposed the cells to electromagnetic fields to polarize the nanoantennas. Some of the cancerous cells, especially those of some types of aggressive brain tumors, showed markedly decreased metabolic activity afterwards. The metabolic activity was also decreased for healthy cells, but not as much. This is all well and fine, I guess, but it's far away from application, and the link to quantum effects is somewhat of a stretch. I mean, as I keep saying, all of chemistry is quantum physics anyway. Though I have the feeling that bio-quantum nanoantennas in the brain could make for very interesting headlines indeed. We've heard a lot about how climate change supposedly drives migration, but a group of researchers from Finland says that it's not the climate that prompts people to leave their home provinces or countries, but rather socio-economic factors, at least for now. In their new paper, the authors collect data for birth and death rates as well as population stats from more than 200 countries. They then compared this information with data from the Human Development Index as well as each region's aridity index. They found that between the years 2000 and 2019, aridity, or dryness caused by lack of precipitation, was not the biggest factor in driving migration. Instead, socioeconomic factors from the overall development of the region had the biggest impact. There are a few issues here. First, aridity isn't the only problem caused by climate change. Second, difficult environmental conditions are correlated with socioeconomic factors. And third, as the researchers themselves admit, many people who might want to leave a region simply can't do so if those socioeconomic conditions are not in their favor. But if a tree falls in a forest and no migration researcher is there to hear it, maybe it didn't happen. Thanks for listening. We'll be back next week.